Welcome again to SAMI KMF and Mathematics. We're going to be entering another very wide area of mathematics that is most applied. I'll be very bold to say that most applied area of mathematics, and that is vector spaces. What do you mean by vector spaces? If you are studying, if you are an engineering student, you already know that vector, we are talking about quantities that have both scalar and direction. We have both magnitude and directions. So, but we are not going to be going into the physics phenomenon of vectors, but we are going to be dealing with the general concept of a vector space. So vector spaces, that's spaces that has to do with vectors. So what do we mean by that? So I'm going to bring this, I'm going to put something like this to make our definition quite interesting. So I'm going to bring this. So you'll be wondering, what is this? No big deal. The V there represents the vector, the set of vectors. So V represents set of vectors. So the V represents the set of vectors, and the plus and dot represent the operation. So the plus represents the vector addition, represents the vector addition, and dot actually represents the scalar multiplication. The scalar multiplication with respect to the field F, with respect to the field F. So sometimes we say that a vector space over a field F with respect to these two binary operations. The binary operation is vector addition and scalar multiplication. So this is what we call a vector space. You can always coin the definition anywhere how you want to put it, but it's very important for you to understand what this means. So this is a set of vectors. So how do we know that this is a vector space? And how do we know that this is a member of a vector space? And how do we pick an element and know, okay, this is a member of a vector space? So I'm going to give you 10 properties that actually makes this a vector space. And the 10 properties are listed as follows. The first property, I'm going to be explaining them, is the closure property. So suppose, I'm going to start with this. I'm going to start with a statement and say, suppose we have U, V, and W. Small u, v, and w, this is capital V, which are members of that set. So this and this and these are actually vectors. Some textbook will want to put arrows this way to show that they are vectors, but I'm not going to do that. I'm just telling you that these are vectors. So these, and these are members of this set, and I'm going to get C and K, which are members of this set. So these are vectors. These, and these are vectors, and these are scalars. Just what I mean by scalars is just example real numbers like 3, 3.26. Another type of scalar can be even complex numbers, but numbers in general. And why we have this as V. So the first point, number one, the first point is closure property. The closure property. What do I mean by this? Anytime you add two vectors in a space, it's going to give you another vector in that space. So U plus V is going to be, so we'll call this the closure property. Number two property is that U plus V is the same thing as V plus U. This is the commutative property. The commutative property is telling you, you can add vectors however you like them. You want to add U plus V, or you add V plus U, it's going to give you the same answer. Number three property is that U plus V plus W, U plus V plus W. It does not really, the order in which you take them does not really matter. So if you want to add the second and third before the first, and you want to add the first and second before the third, however you want to add them, it's okay. So this is closure. This has to do with commutativity, and this has to do with associativity. So this has to do with associativity. For we have the element I will call the zero element, that is the zero vector, such that when you add it to any other vector, it is going to give you the vector itself. So that zero is actually in V. So this is actually referred to as a zero vector. It is a zero vector. That's what it really is. Zero. 5 is the negative vector, this negative vector in this, such that what I actually mean is that if you add v plus minus, if you had u plus minus u, it is going to give you 0. And that 0, we've already said, is already here. So this has to do with the identity element. It's kind of identity because when you add anything to it, it's going to just return the same thing. This one is a inverse, kind of the inverse vector, something like that. Inverse, yeah. So this is going to give us 0. Then we have some other properties I'm going to add to that. And what are the properties? It has to do with the scalar. I'm going to do something like this and you wonder, what are you doing? When you multiply a scalar multiplication I'm talking about, with a vector, it is still going to give you another vector in this space. So it's going to give you, you just take a number and multiply it with a vector, it still remains a vector. So this is still the closure, kind of a closure property. So this is kind of a closure property. You pick a scalar and a vector, and it ends at giving you another vector, probably an enlarged, reduced vector and magnified vector. Just transformation. We have another property where you add 2 scalar with a v to give you cv plus kv. So this is another property, has to express linearity. So, but anytime we talk about vector spaces and we talk about linear spaces, please, we are saying the same thing. A vector space is different as a linear space, just terms. So 8, we have another property that's very important, and that property is a case where we have just one scalar and we have v plus u, and that is going to give us cv plus cu, so something of this nature. And we have another property where you can simply multiply 1 times a vector, and that will just give you the vector. So 1 here is more like the scalar 2, but very unique property. You have 1 multiplying 1 times v, and you end up having v at the end of the day. So we're saying that the identity in this case is simply 1. So this property 9 property actually gives you, actually is a property that verifies that you are in a vector space. So if a vector can actually satisfy all this, then we say that that is a vector and it's in a vector space. But 9 to 10 properties are actually too long, and we may not be able to check this all the time, all these axioms or theorems all the time. So what we do is to learn vector subspace, vectors per subspace. So before we go to vector subspace, I'm going to give you examples of vector space. An example of vector space is G N L R. So this is an example. Matrices. I'm sure you're shocked, but matrices actually represent the set of this. This is a vector space. This is a vector space. What I mean by this, a vector space, is that all matrices satisfy all these properties. Very, very interesting. You can add matrices. You can operate associativity on matrices. You have the zero matrix. You have the zero matrix. Something like this is actually referred to as zero matrix. You have all these work on matrices, and it's very interesting. You can multiply a scalar with a matrix. You can have something like 3, 4, 2, 6, and 1, and that will give you 12, 6, 18, and 3. See, this is another matrix. So all these properties are satisfied when we're talking about matrices. Another type of vector space is the set of polynomials. Yes, the set of polynomials are actually referred to as the vector space. The polynomials, for instance, p of x equals to an x is per n, an minus 1, x is per n minus 1, that up to ax and a naught. So this is the set of polynomials. Isn't it shocking that actually a polynomial is actually a vector? Very, very interesting. All these properties will be satisfied with a polynomial. You can actually add polynomials, switch them, operate associativity on polynomials. We have the zero polynomial, which is actually 0. You actually multiply a number with a polynomial. Just multiply a number with this. It doesn't change it from becoming a polynomial. If you multiply this with a number, it still becomes a polynomial. And what else again? You multiply 1 times a polynomial, you're still going to land at a polynomial at the end of the day. So all these properties will work for a polynomial. Very, very interesting. So we have so many other vector spaces, we have space of continuous functions, functions that are continuous. As long as the function you have f of t and f of t is continuous, it becomes this, it becomes v, this becomes v in v. So space of continuous function, I can't name all, there are so many. But in the part 2 of this video, I'm going to talk about vector subspaces.